I scheduled a
Stage two.
Oh,
We're still talking about circular motion. You guys worked on this a little bit on Friday. Let's look at the solution.
Yeah, we have an immuno test next Wednesday.
So a couple of things. The radial acceleration.
He's barely talking about it.
It's going to be a meter per second squared.
The success as well.
So the first thing I have to do is say, well, I have a diameter. So 2 meters, the change up is 0.12 meters. And I know that I'm going to be working with a radius. Your radial acceleration is r over the square. Radius. Diameter. That's 0.06 meters. Now, revolutions per minute can be turned into revolutions per second, which is what? Frequency. That is frequency. What is it going to get you about 120 hertz? 100 hertz, a couple of ways to look at this. Per seconds, which is 1 over seconds, which is also revolutions per second. So in most textbooks, you'll see hertz as inverse seconds because again, revolutions and radians aren't going to come in as a unit. It's just letting you know something that's happening per second. Now, we need the angular velocity. What are the units of angular velocity?
I don't know.
I go from revolutions per second to what? Radians per second.
I got this word down, just none of these letters.
So that means I'm going to have to do 2 pi times frequency. And that is going to give me
And if I did this in trace back.
yes. Because again, if you wanted to do that, your omega is radians per second. So let's look at it like that. I'm doing these so that you can see the actual definitions of things come in. So it's like there's your definition of your radial acceleration. But if you wanted to do it that way, you start with 3,200 revolutions a minute. Seconds, and then, yep, there are 2 pi radians for 1 revolution. And when you, and so then of course all the units on top of bottom that are the same will cancel out. You have radians per second. I want to make sure that you're equating radians per second with angular velocity. And then from there, We already have the expression for this. 106 meters. 154 radians per second squared, and we get an angular a radial acceleration 3.41. Instead of 4 meters per second squared. Well, let's see. So some of the problems in textbooks now have yeah, like this is a problem about a compact disc. But what, a couple of years from now, a problem about Blu-ray or a compact disc, everyone's doing it. Well,
It's cheaper than having a streaming service.
but it's actually kind of hard to get a Blu-ray player or a DVD player.
I have a DVD player.
Sucks.
I just got one. And then at garage sales, they just give away movies for free.
Over the past month, I cut off a lot of my streaming services. I tried to watch Netflix here on campus. And I said, well, this isn't on the network in your house.
The household?
You're gonna have to pay for a separate membership. I said, okay, well, you can shove it, because in capitalist society, when I'm paying for a product, I will decide what I do with that product.
No, that makes me mad. My mom, like, I'm signed to my mom back home and it gets mad at me. Like, it's like, you're not in your household. That's why I won't pay for it. I'm a college student, my mom's paying for it.
Yeah.
I watch cartoons on YouTube. They have Mickey Mouse full
So
episodes.
is the
on
down
it.
thing
I watch
like
old
this?
cartoons that nobody remembers, they were from my childhood. So like along to the 90s, 80s to 90s, there was this Ghostbusters cartoon. I watched that.
Moved it over.
Yeah, we're talking about uniform circular motion. We're gonna talk about both uniform and non-uniform circular motion. There's only one difference between the two. Uniform circular motion means your velocity is exactly the same at every point around the circle, your linear velocity. So do you remember what linear velocity is?
The tangent.
Yes. So if you had an object going around the circle, your linear velocity is the tangent coming right off that circular motion at that point. So uniform circular motion, that velocity is going to be the same all the way around the circle. Now, let's take a look at this problem here. Okay, so what does this sound like to you? Wooden force located 8 meters from the center axis. Oh, it tells you carousel. Never mind. And so the wooden force moves at a speed of 6.0 meters per second. This thing, many of you were very young, the radial acceleration that kept you all alive was the strength in your arms, because how many of you got on the merry-go-round, they sped it as fast as they could, you're just holding on.
Yeah.
I dislocated my knee.
Oh, special.
We used to play a game during recess, see how many people would be fling off the merry-go-round.
Yeah, but then they took it away, like when I was in elementary, so people got injured. This is happened with the tennis ball.
My school broke the merry-go-round doing
We
that.
didn't have swings at our school because people kept with
You
them.
didn't play dynamite with the ball?
I was like in kindergarten when I played with the tetherball pole, and then they took it away, so I don't really remember what I did with the tetherball pole.
So here's the force acting on the child, sitting on the horse. The child's weight is 130 newtons. Okay, so let's think about this.
Me and my siblings' initials are actually like a bougie.
Trying to draw a circle and profile.
It's stupid.
Not as fun. That was not safe. How's this
Now
supposed to be
your
safer?
force
How do you?
there.
Yeah, I'm actually impressed.
There's the center of your circle.
I know, but like, someone's supposed to push me somewhere.
So one thing that we know, imagine you're looking at this flat, like this is a flat circle, it's going round and round. You have a radial acceleration inwards. That's keeping you from being flung off the carousel. Then you have a radial velocity of 6.0 meters per second. Okay, so the sum of forces we're predominantly worried about the forces in the radial direction. Okay, I'm switching back and forth between R and C again. What is C? Centripetal. And again, make sure you don't confuse the two words. Centripetal means towards the center of the circle. It's the force that holds you in a circular path. Centrifugal is the force going the opposite direction, trying to free you off the
Can
circle.
you spell up there the actual word?
I will try.
Wait, and the
Do
C
we need
stands
to know
for
how to
which
spell?
one?
Centripetal.
Which means what?
The one that's keeping you on the
Towards
circle.
center.
It's keeping you on the circle. The other one is flinging you off the circle.
Yeah. So again, most of you are familiar with centrifugal force because in chemistry labs you've used centrifuges.
So is that AR, that little r? Could that also be?
Yeah, it could also be AC. So when we say radial, we're talking about the centripetal force, the centripetal acceleration,
Towards the center.
and it's moving. So we have a mass times a centripetal acceleration. Now, when you're setting positives and negatives, I found an easy thing to do is set positive towards the center of the circle, then negative as the other way. Instead of thinking of it, and once you get back into linear, you can think of it in X and Y. But if you're trying to think of X and Y, when you're going around a circle, that X and Y are going to be constantly changing by some angle theta. So it's going to be it's usually best to try to set positive towards the center of the circle. So that means centripetal force is towards the center of the circle, it's positive, equals the mass times the centripetal acceleration. And then we have a definition, remember we did this earlier, AR, AC, equivalent, and equal E squared over R. So then we get M E squared over R. Well, we don't have mass. How do we find mass?
Use the child's mass.
Right, so we say that the gravitational force on the child is the mass of the child times gravity. Mass will be the gravitational force divided by gravity. So that's going to be 130 newtons divided by 9.8 seconds squared. This child is going to be 13.27 kilograms. Kind of a small kid.
Tiny baby.
So now that we've solved for the centripetal force, plug in numbers. the linear velocity, because again, remember, anytime you see a v that's linear velocity, omega is your angular velocity. And we end up with a radial or centripetal force of 59.7 newtons. Okay, so far, how has the math been in this chapter?
Did the problem. So
That's fine.
Because what do you think happens when you combine rotational motion with linear motion?
it's gonna get harder.
Okay, so we're gonna do a little exercise here. Okay, so you have a system here. Like, is anyone in track and field?
No.
Nobody? Okay, so this is, we're trying to figure out what the hammer throw, what they have the hammer on the cable, they spin around until they get a velocity and then they fling it. Okay, well, when they fling it, it has an initial velocity and it's going in X and Y. That's projectile motion. You can extrapolate backwards to the initial velocity. And then that's going to be your linear, velocity off of your angular motion. You can use that for your centripetal force. So what is the force of the tension of the cable as you're spinning the hammer? Now, let's just look at the projectile part, okay? So as you read this problem, you're going to have a motion like that. Because of course, you're holding the hammer about a meter off the ground. When it lands, it's going to hit the ground. So it's going to fall through that additional meter. Well, set the ground is y equals 0. Then you'll have to know if that delta y is positive or negative. So what I'm going to tell you is you're in X and Y. You're going to have an initial velocity. Yep. So it has an angle of 40 degrees. So then what we need to do is we need to combine that kinematic and that kinematic to solve for the initial velocity of that flight. So you start with those two kinematics, that's where you're gonna end up. Now get in groups and figure out how. Yep, you're trying to derive this initial velocity. Because this initial velocity is going to be the velocity that the hammer leaves circular motion with. So you're then going to be able to use that velocity, that linear velocity, to figure out the radial acceleration while you're spinning the hammer.
One of these actually, she said, are you kidding? Make X and Y equals the initial velocity. It's terrible.
This one is for delta T.
This is a good practice for projectile motion because last week's assignment was motion in one direction. This coming week, you're going to have several problems on two-dimensional projectile motion. No, there's not. Pay attention to, you don't have a time of flight, so that's a little problematic.
Oh, yeah, so we should solve for time of flight.
Then plug into the other one.
Here. Are you just gonna use that first equation?
I think so.
So it's just-
I know.
Of x, which we know can be squared with gravity, x. And we take out t squared by making.
Which would be our,
But I still don't understand how we got control x.
Like that.
right? Don't we start at 0?
I would say that there. Yeah. So maybe we need to separate the.
You and I get in shape.
That divide by-
Yeah, I did.
I have that. I said why. Trying to catch up.
Grace, I've already done
The same. But delta T is time.
That's literally.
We know that it moves from
All you can do is
0
tell it.
origin to 70.
You see why I put the annoying word on?
400 stand there. Who else is gonna do
So you're trying to get rid of it, right?
Yeah, but you don't need that yet. You just need to solve, you need to hit that equation. Yeah, the delta x is in the problem.
So we can find delta t.
Well, you don't have a delta t. You don't have a delta t. You need to find out how to get rid of it.
But we're not trying to solve it.
Nope. Well, in a way, yes, but you're not gonna have a number for it.
It just happens.
Do we need to set something up to get the delta x and the delta y?
That's some algebra with a little trick.
This one.
Literally 8 years ago.
I'm not even kidding.
I saw a funny joke today, but most people wouldn't get it. I said that physics is something where you can mathematically figure out every point of a process. Magic is something where you have no idea what the process is, but you know the final outcome is like you're cursed. Now that we know that thermodynamics is magic.
Oh.
What's the chances of 2 cosine theta being connected after those two?
Very good.
Okay. Okay. So we need to actually multiply these in,
They would need to
To solve
solve
it?
this backwards.
like multiply those chairs.
Solve it backwards.
Does that mean you know that we're doing square?
So that'll become delta x squared over vi squared cosine squared theta.
And then I'll just multiply.
Yep.
Are you on the right path?
Yes, I'm gonna multiply those and squared and then.
Wait, don't that make them even to each other?
I think we will just run off.
Can we do that
I feel like some
before?
people have already thrown in the towel.
Different test?
Yeah.
Can we do that?
Monday.
No idea.
Yeah, I was thinking about that when I came up with this exercise.
2 cosine.
I just don't. Delta T on its own correctly.
I think I did.
Delta y.
You know, I've never seen anyone snack on pea pods.
Yeah.
Are they?
Is it?
Do you want one?
No, thanks.
Why?
No, I'm good.
Yeah, a couple of them are early.
Yeah, in this town, it's kind of hit and miss finding good produce.
Yeah, I'm really good. This one's not bad.
That's the way to do it.
I'm so confused.
You got me fired up. A little bit of
I mean, should just cancel it.
Remember, there comes a point where delta y is multiplied by 1.
Like the pasta, like dinner and lunch.
It's a little physics trick. It's multiplied by 1. See, because then you only have to do it to one side of the equation.
The multiplying by 1 equals
It would be-
so it's considered 1.
Mhm.
I like breakfast.
I don't know. I don't know.
Then you have to figure out how to make both of that, how to make 2 fractions have the same denominator.
I don't know.
They make such good sense when you go over them and then you like say
And
you
when
do it by
it's my
yourself and I'm
turn,
like, I don't even know.
No, that's why I kind of like let you struggle with it for a little bit. Then we go through it and then you can see.
I set them equal to each other.
Maybe. This is more like a system of two linear equations.
I figured out.
Oh, well, I wanted to factor out the BI because you were talking about wanting to get the BI out of there somewhere.
Yeah, you can do that.
You need to find a way to like,
You get 357.
you need to find a way to get the BI by itself.
270, 275. So yeah,
You're on the right track.
what do you think you can get to?
Or is I go on a Monday?
Okay, who's given up already?
Me.
I'm getting close.
Okay,
You did the best.
so couple of things we don't know. We don't know delta T, so that's gotta go away. There's no x acceleration. And also, realize that initial velocity, well, no, we'll get there. So do you notice how this velocity has components? That's gonna have to come into play. Say
I
delta
made
T.
components. I did.
That would have helped a lot if I would have known everything else.
Over. Well, we've been talking quite a bit about no acceleration in the x direction.
No. It's just like, it didn't go very well.
Now I can substitute this in for delta T in the kinematic equation in the y direction. Oh, we're going to substitute in delta T. And so the acceleration in the y direction is a minus g. Okay? So we have to take account of the fact that there's the initial velocity we're trying to solve for. Now we can substitute these in. A couple of things we can do. Initial velocity there cancels out. And we can then bring that squared inside and square everything in there. Do you remember how squaring works? How do we do it? Remembering how fractions work?
No.
Okay, so let's start trying to separate some variables here. Okay, so I can say, so this whole side is delta y. So I can say delta y minus that. Then that is a fraction. We go ahead and multiply it through by -2. Now, the left side of the equation, to get to where we need to be, I really want that to be one fraction. So, to be able to add or subtract fractions, I have to have the same what? Denominator. How do I turn 2 delta y into a fraction with the same denominator?
Divided by cosine theta.
I have to multiply by 1.
Multiply by 1. What do you mean? That's oh, yeah.
Cosine theta over cosine theta is 1.
Where's my cosine?
So this is gonna be alright, we're getting closer. Now I'm gonna multiply through by the initial velocity squared cosine squared theta. And then what you see here is I have cosine in the denominator. I get rid of that cosine squared. Now I'm going to divide through by the 2 delta x sine theta minus 2 delta y cosine theta. And we pull that 2 out front. I'm going to divide through by the cosine theta. And then I end up with the square root of the whole thing. One second. And so we end up where we need to be. Now you'll see the author of the textbook end up at this equation. But he doesn't show you how, he doesn't really show you how he got there. He expects you to be able to figure that out. Now from here, you could go back up to the problem, grab all your numbers, plug them in. Let's look at some of the numbers in the problem. 40. Delta x is 74 meters. The delta y is going to be a -1. You know why?
Our final is 0 and our initial is 1.
Right, because the ground is 0. It starts at your initial y is 1 meter up. So final minus initial, 0 minus 1. Then we're going to plug all those numbers in here. And you're going to play with your calculator. You should get 26.9 meters per second. So of course, gravity is your 9.8. You plug in all those numbers, and you end up with the initial velocity. Now, this is the linear velocity that was achieved by the athlete swinging the hammer in a circular motion. So now you have to take this linear velocity and put it into a rotational motion. Okay? So, the athlete swinging the hammer is swinging in a circular motion. And tension in the cable that they're swinging with. Now you also know when you're thinking about the sum of your forces, that there's mass times gravity on the hammer, but this is where physics can make a generalization. You know that your tension is much larger than the gravitational force. Because again, if you've ever swung anything, you see how it stays up. So that radial acceleration is so much greater than the gravitational force, we can neglect the gravitational force. Because again, if you were swinging something around in a circle, it's not going to fall. So that gravitational force becomes negligible. So then what we say,
Gonna get downfield routes now.
We see the way tension is pointing towards the center of the circle, so it's positive. Centripetal acceleration or radial acceleration is positive. Remember that centripetal acceleration, E squared over R. And so now, this is where, so what the mass from the problem is 4.08 kilograms. The velocity we just solved for and the radius of the swing, that's going to get you attention. So that is the force being applied to the hammer by the athlete. Now you notice how you first had to solve the projectile motion and bring that linear velocity in, because what you can imagine your linear velocity is coming straight off that circle. And so as soon as the athlete lets the hammer go, it goes with that velocity into a projectile motion. So once you have that initial velocity, let's take it back into the circular motion and solve for that, that force, the centripetal force, the radial force, whatever you want to call it. Okay. Now, what if you're traveling on, around a curve and you have banked versus unbanked curves? Let's talk about the unbanked curve and then we'll call it a day and we'll compare it to the banked curve next time.
It's a banked curve.
Think of a racetrack, how the curve is on a slope.
Oh, I see.
So imagine you're on flat ground, you're going around a curve. Okay? So you're just on flat ground. You still have your linear velocity, but you're moving in a circle. What force is keeping you in that circle?
Centripetal.
Yes, what is the centripetal force in this situation? You go around a curve on a road, what keeps you from sliding off?
Friction.
Friction.
Oh,
Friction is what holds you in a circular motion,
There's like a
particularly static friction, because you want it to be static because you don't want to be sliding. So for an unbanked curve, it's the static friction force holding you, that's your centripetal force. So next time we'll talk about a banked curve and how the force changes a little bit.
Wait, unbanked curve?
So this is unbanked.
The uncome from.
Wall.
A wall?
like there's not a wall.
Like a bank, like. Yeah.
Yeah. So this is just on the unbanked is just on flat ground.
Wait, why did you need to figure this out, Evan? Yeah, but like, in what circumstances do I do it? Not even in a way I don't want to learn it.
Now, all of you are great drivers, so maybe you need to know.
What? Why would you assume that?
And like for example, your coefficient of static friction goes way down when it's raining.
I'm an excellent. I always use my cruise when it's raining and my dad said you should not be doing that. I said, I don't care. I got my license. I don't.